Alright, so now we're going to look at other bases besides E. So we can start here. We have these four techniques. We talked about some of those before. So this to this power equals that, base, exponent, answer. So 16 to the x equals 8. So if we look at our options over here, maybe the same base. Hopefully we recognize both of those as powers of 2. So this would be 2 to the 4th power, and then to the x. So then when you have a power to a power, you multiply, and then 2 to the 3rd power. So here the bases are already equal, so we can just focus on the exponents, or you could take the natural log of both sides and bring those down and then divide by the natural log of 2, and those would cancel out if you want to see that process a little differently. Some students have a hard time kind of what happened to the 2's. So like I said, take the natural log of both sides, take that out, and you can divide by the natural log of 2. I just switched my focus to the exponents because the bases are already equal. So the answer is 3/4. Alright. Now in this one, when there's no base given and it's not an ln, then that's the common log. That's base 10. So that's going to be 10 to the x power equals 0.01. But 0.01 is 1 over 100 or 1 over 10 squared, which we could write as 10 to the negative 2, in which case we're focused on x equals negative 2. Okay. So over here we just have it written out, and to focus on this to this power equals that, a to the n equals x, just kind of showing us that rewrite process. Alright, so down here, what can we do with this? Now, we could get this to be a power of 2. That's not a normal power of 2, but we could do it with a decimal. 2 to the 5th is 32, and 2 to the 6th is 64, so 2 to the 5 point something, but we would be approximating, so we don't really want to do that. So one thing we could do is we could take the natural log of both sides, and then we can use the properties of exponents to bring that down in front. So we would have 3x natural log of 2 equals the natural log of 50. And then we could divide both sides by 3 natural log of 2. So we'd have the natural log of 50 divided by 3 times the natural log of 2. Okay. Here, this is kind of focusing on the inverse idea. So if we take the r in here using the properties of logarithms, and then we have e to the natural log, those are inverses of each other, and so we get a to the r equals a to the r. Again, just these two things here, just kind of reinforcing some properties and techniques. Okay, now we want to look at this half-life question, except we want to modify it a little bit. So we're going to look at it two ways. So first of all, let's look at the kind of pre-calculus Algebra 2 honors way to solve this question. So we have the amount, you can read that, hopefully you kind of remember, you've heard about carbon 14 before. So the ending amount is equal to the initial amount, and then the half-life means half of it is left, and the time divided by the half-life of carbon 14, which is 5,730 years. So what we're asking is how many times has the half-life happened. So if it was 5,730 years, then that would be 1, and we would be multiplying by 1/2, taking half of it. Okay, so if we want to look at the fraction that is left, we take the resulting amount divided by the original amount. So that looks like that. And then what we may want to do here is take 1/2 to the 1 over 5,730 times t. So that's how we want to look at that. Now what we're going to do with that is switch it. In calculus we focus on using e and the natural log. So if we take this and we raise e to the natural log, because these are inverses, so we really haven't done anything there. And I'm going to switch 1/2 to 0.5, and we've got t over 5,730. Okay. Now, if we bring the exponent down in front using the properties, we're going to have the natural log of 0.5 divided by 5,730 times t. And so what we get there is that ratio is approximately e, and if we do this on the calculator, we get negative 0.00012t. So in calculus, we're going to focus on the formulas in this format, and we'll see if that what difference that has on the problems. So this is just a little bit of background information. I guess we could have done that before this problem. This is not really, I mean, we are setting it up, but so we're going to compare the two. So the first thing is, if you think about 8,585 years compared to 5,730, well, so we can tell that the half-life has happened once, but it has not happened twice. So if it's happened once, we know there's less than 50% left, but it hasn't happened twice, so it's more than 25. So we know it's going to be somewhere between 25 and 50%. Okay? So that should help us as we think about our answers there. So if we use this formula and we do 1/2 divided by, or not divided by, to the power of 8585 divided by 5730, and we do that in the calculator, and you might want to type that in your calculator just to make sure you remember how to input that stuff, we get this. But if we use this formula, so we take e to the negative 0.00012 times 8585, then we get 35, which is the same, but then we get 694%. And that's going to be more accurate because of the more accurate, the exponential is going to be more accurate than this. That's why we use it. Okay. So, and that's technically all still kind of Algebra 2, pre-calculus. Usually in pre-calculus we would talk about both of these things, and you would see some of these in your textbook as the examples. So here we want to use the same base, because I recognize that 32 is a power of 2. So that's going to be 2 to the 5th, but it was a fraction, so it's going to be negative 2 to the negative 5th. And we're going to set those equal to each other. So, and I'm going to divide by -1, or multiply by -1, either way. So we're going to get x equals 5/2. Okay, last one before we switch to some calculus. Here we want to use the properties of logarithms, so we want to put these together. So that's going to be the log base 4 of x plus 3 times x equals 1. Now we want to rewrite that. So we're going to do this to this power equals that. So 4 to the first power equals, we'll go ahead and multiply that out. That's going to be x squared plus 3x. Set that equal to 0. And factor that. So probably this is negative, so we have a positive and a negative. So we need to subtract factors of 4 that subtract to give 3. So plus 4 minus 1. So we're going to have x equals negative 4 and x equals 1. However, if we plug a negative 4 in here, we have the log of a negative number and the domain of a logarithm. Let's focus on this one. The domain of this would be x has to be greater than 0. So that's not going to work out there. Okay, so now let's get to the calculus. And this is pretty rare on the AP test, maybe one question, but if we compare this to the derivative of e to the x, we can see what happens. So if we take the derivative of e to the x, we get e to the x. We just get it back. So if you apply this formula to it, you say, well, why are we doing this? So we have a to the x. That's equal to the natural log of a times a to the x. So that part's the same. So the derivative of e to the x is e to the x, right? But what about this? If we follow this same, it should apply, this formula should apply to this also. So that means that we would have the natural log of the base times e to the x. But the natural log of e to what power equals e to the first power equals e, this just equals 1. So we didn't write that down because we didn't need it. That was going to turn into 1. If it's any other number, the base, then we're going to need that natural log of a in front of there. But what you can do when you see one of these is kind of think about this and test it out to make sure your formula is correct. Alright, so if there's something else there, just like if the derivative of e to the x or e to the u is e to the u times du, we have the same thing here. So if we have a to the u, we're still going to get the natural log of the base times whatever this is times the derivative of the exponent. So that's the chain rule there I want to use basically. Okay, now this one hopefully is not too bad. What I want to think about here is the change of base. Change of base rule. So the change of base rule says that you take the log of the thing that's higher over here, x is higher than a, so the log of x and the log of a. And if you look at that, the log of a is going to be a constant because they're going to give you the base. So that is 1 over, and actually though, darn it, when we do the change of base, we can use any base we want. So normally on a calculator in pre-calc classes, a lot of times we switch it to the common base, but I don't even need to do that. I can do this. That's the same as the natural log. Okay, and so then the last thing there is we're going to have 1 over the natural log of a times the natural log of x. And the key here is this is just a constant. So the derivative of this is that constant, 1 over the natural log of a, times the derivative of the natural log of x. Now remember, this is a variable, this is a constant. So the derivative of the natural log is 1 over x. So instead of memorizing this formula, if you already know the change of base process, you can use that, and then you don't even really need to memorize this over here, because it just works out. And then here we get the same thing, 1 over u times du. So that's not really anything new there. So if we try that out here, find the derivative. So the derivative is going to be y prime, or dw in this case, because they're w's. So we have a different base here. So normally if that was e to the w, it would just be e to the w. But now because there's a 4 there, we're going to need to have, and hopefully you pause this and try it out. So the natural log of the base, and then just the same thing. So it's going to be times 4 to the w. Now over here, minus, so remember this, if we use the change of base on this, just like I talked about up here, we have the natural log of w over the natural log of 7, which turns into a constant. So we would have 5 over the natural log of 7, and then the natural log of w, the derivative of that's going to be 1 over w. So that's what we would get there. Okay. So here, let's try this out. Now that's just a constant, so that's not going to do anything. So we have 2. Well, I mean, it'll be there, but so the derivative is y prime. Derivative 2, nothing's happened there. The derivative of a different base besides e, we need the natural log of the base times, and then the derivative of an exponential is just the exponential after we've done this part. So that's going to be 3 to the x. And then that's a constant, so we just write it down, and the derivative of e to the u is e to the u du, but du is just 1 here. The derivative of x is 1. So there we go. Now, finally, here, let's see. So our base is 3, so we're going to have the natural log of 3, times, it's an exponential function, so you write down the exact same thing. And then, because you have a function in there besides x, you have to use a chain rule. So the derivative of that's going to be 4x. And not really anything, we could rearrange that a little bit, but it's not really going to help much. Okay. Alright, so now we're going to integrate exponential functions with bases other than e. So when we took the derivative, we multiplied by the natural log of a. So when we integrate, we're going to divide by the natural log of a. Otherwise, it kind of fits that same pattern as the integral of e to the u is e to the u. If you're not sure what to do when you see an integral problem like these, your best bet is to either rewrite it or use u substitution. Okay? So when we look at this, maybe what we can do is let u be negative x. So du is going to be negative, and so dx is equal to negative du. So that's going to be negative 2 to the 4th du. Okay, so we're integrating. So we have a few things going on here. So first of all, that's negative. Now when we integrate this, we divide by the natural log of the base, and then we just write down whatever we, oops, that's not supposed to be a 4, where'd that 4 come from? That's u. So that's going to be 2 to the u, but I'm going to go ahead and just plug that back in. And then don't forget plus c. Alright. So you look at this integral. Now there are 2 terms in the denominator, so that's not that. Maybe some of you think, oh, we could split that up. No, it's only if this was flipped over, then we could do that, but not here. So it's probably, you're not sure what to do. I'm not really sure how we could rewrite that, so it's probably a u substitution. So we usually let u be a little bit more complicated thing there, or something inside. There's not really an inside there. So that's going to be 2 to the x plus 1. So now if we take the derivative of that, the derivative of this is going to be the natural log of 2 times 2 to the x dx. Now we can see there's a 2 to the x dx right there. So what we need to do is divide both sides by the natural log of 2, and then this matches up pretty nicely. So the 1 over the natural log of 2, we'll factor that out. And we have the integral. Now this is going to be u, 1 over u, and that's going to be du. This part right here is du. Okay? So if we integrate 1 over u, this is good practice for our other lesson, the integral of 1 over u is the natural log actually the absolute value of u, which was 2x plus 1. And then we have this natural log of 2 right here. And don't forget the c. Don't forget the c. Don't forget the c. Okay? So, once again, we have an integral. It looks kind of scary, so we need to actually, if we look at this as a composite, it's a function inside of the function because we have e to the x, but then we also have the square root of x. So when you have composition of functions, then that's a pretty clear indicator that you need to use substitution. So our substitution is going to be for that exponent. We're trying to, anytime you have an e in an integral, you're probably trying to get e to the u. So there's u. du is going to be, bring the exponent down, subtract 1 from the exponent, dx. Okay. So now, if we look at this, dx over x to the 1/2, that's right here. So if we multiply by 2, we'll get 2 du, and then if we leave this, that looks like that, which is nice. So we can bring this 2 out here, and this du right there. This is equal to 2 du. So there's 2, there's du. Now here, we have e to the u. So the integral of e to the u is e to the u. But u is the square root of x. And then don't forget plus c. So that u substitution, I told you that lesson was pretty important. That assignment was pretty important to go back and practice and do those odds and make sure you know what's going on there. Okay, so example 5, be careful. So I've talked about that before many times. If somebody tells you to be careful and you don't know why they said be careful, then that's not a good sign. So if you're looking at this and you're starting to do some work and you're like, oh, what's the problem? That's easy. You probably got it wrong. Okay? Because you should say, oh, I see why he's saying be careful. Okay, so this is not 5e to the 4th. This is a constant. E to the 5th is that's 2.71828 to the 5th power. So this is just a number. So when we take the derivative of a constant, we get 0. So that's it's kind of like if I had pi to the 5th power. The derivative of pi to the 5th power is also 0. Okay. Moving along, this next one is called logarithmic differentiation because when you look at this, and we want to take a derivative here, it just gets, it's a little bit messy because our normal rule is you bring the exponent down, you subtract 1 from the exponent. It's just a bit awkward there. So what we want to do here, is take the natural log of both sides. So if we take the natural log of both sides there, what that allows us to do is use the properties of logarithms, and we can bring that down in front. Okay? So now we have the natural log of y, and we have this times this, so that's the natural log of x squared. Okay? So now if we take the derivative of that, we're going to get, now this is implicit differentiation because we have stuff, so the derivative of this side is going to be 1 over y dy dx. The derivative of this side, you bring the chain rule here, so you bring the 2 down and subtract 1 from the exponent, and then you do the derivative of the inside, so the derivative of the natural log of x, that's 1 over x. Okay? So if we multiply both sides by y, we have y times 2 times the natural log of x over x. Now y is actually right here. So we can substitute that in for y. So we're going to have, I don't want to write that. We're going to have x to the natural log of x power, that's y, times 2, I'll bring that in front, times the natural log of x all over x. So, a little bit strange there. Okay? Now down here, this is the interest formula with money that maybe you've seen the last 2 years. So N is the compounding period. So how often do you get interest? So I know I have accounts that give interest once a month. So the compounding period is 12 times per year. Compounding period, the number of times per year is what we're looking at. And then R is the interest rate as a decimal. So that's what we're looking for there. Now this whole formula, or not the whole formula, but the part I have highlighted in yellow, can be adjusted to e to some power k times t, which leads to the PERT formula, which again, they're just going to use k instead of r. It's basically the same thing. So that's what we're looking at there. So we're going to use that a couple times now real quick. And the way they expressed that was they would have said this was compounded continuously. Okay. Alright, so this is just a pre-calc problem here. Actually, there's not a lot of calculus on this last page, but just a little review. So, quarterly. So our interest, our amount that we're going to have, we invested $3,000, and 1 plus the interest rate is 6% as a decimal, that's 0.06. Compounding period is quarterly, quarter, 4 quarters, and $1, 4 quarters of a year, 3 months at a time. So that's going to be 4. And then up here was NT, so 4 times per year, and then 10 years. So you're going to get interest 40 times for that. So you can type that. For not a bad idea to type these things in the calculator. Make sure you get these same answers that I'm writing down. Not necessarily all 3 times, but at least maybe once, just to make sure that it's coming out the same. Okay, so weekly, that's 52. So 0.06 stays the same, and we have 52. And hopefully it makes sense that the more times you get interest, probably the more money you're going to be getting, because you're going to be getting interest on your interest more frequently. So that one's going to be $64. So, not a lot, but still $22. That's maybe a nice meal for one person, an okay meal. Okay, and the last one is compounded continuously. So that's the principal still, the initial amount, and then e to the RT, the PERT formula. So, and then this one should be the most money. So that is just $2 more. So at some point, as we increase the compounding period, the total amount, the change, becomes less, the amount that we're increasing it by. Okay, so I don't know if you talked about logistic. I think maybe we talked about that in pre-calc. It's been a long time since I taught that class. But so we probably are all used to exponential growth. We've seen stuff like that before. So that's when something's looking like this, usually right before a big fall. Housing prices in Nevada back when you were in elementary school were going crazy, and then anyway, so what we want to look at here is what's called logistic growth. So with logistic growth, what happens is you start off pretty slow, and then there's this exponential, it looks exponential period, but then there's this tapering off period. Okay, and what's happening there is that usually, most situations, this up here is called the limit to growth. So there are things that slow down. So if you have like a carnivore predator situation, and they become very successful, and they start eating all their prey, and there's not as much food to eat, then they're going to start to die off. So they're not going to be able to keep growing the population exponentially, like some wolves in Yellowstone, for example. If there starts to get too many wolves, they're going to start to eat most of the food, and then some of the wolves are going to die of starvation because there's not going to be enough food for them because they're eating it all. Okay, another example is here in Las Vegas. We have a lot of limits to our growth. Water is one of them. Normally I would pause and I would ask you guys to give some of these. So water could be a problem for us that limits things. We have Lake Mead to the east and Red Rock to the west, and we have the Nellis bombing range to the north, and then the California border to the south. So there's a limit to how many people, even geographically, although I guess you start building skyscrapers or whatever, but still, there's going to be some things that that limit us. So the limit to growth is normally the numerator of the equation. That is the thing we're looking at there. So if we compare these, this is a 106-year difference. So that is the amount of time that elapsed, 106 years. Alright. So pretty basically here, the question says estimate the maximum population. That's pretty much right there. So the max, we just write the number down. Now we could look up on the internet if that's correct or not, or what happened there. One of the problems for Dallas is they have Fort Worth right next to them, so there's that boundary. And then it asked for what was the population in 2006 according to this formula. So if you plug in 106 in this formula and calculate that, probably should put a parenthesis there when you type it in your calculator, and that turns out to be 1,181,346. Okay. And finally, this little graph here, and graph this by hand. So if you plug in -2, so -2, absolute value -2 is positive 2 to the second power is 4. -1, that's going to be 2. 0, that's going to be 1. 1, that's going to be 2 again. So we can see 4, maybe do one more. 3, that's going to be 8. So if we do that, -2, 4, and then, just kidding, let's see, some -1, 2, 2, 4, 3, 8, and then 1, and then 1, 2, 2, 4, 3, 8. Now, it kind of looks like a parabola, but it's not. It looks more like actually the shield, Golden Knight shield maybe, because it comes down like that, but then there's a sharp point here, because technically this would keep going like that, or like this. But the absolute value is what turns it back the other way. So there's a sharper point right here, not the normal curve that we should get. Although a lot of us, when we graph parabolas, they actually kind of look like that because we don't curve it. We really should curve the vertex through there. Anyway, it's about that time. Have a good day.